the following table gives values for the velocity of a particle moving along a straight line could the graph at right be a graph of the position of the particle? So here's the chart. And here's the potential position graph. And it starts out like this. That kind of curves up over there, flattens out, curves back up again. So, one of the key things to remember, velocity is the slope of the position graph. So what this means is that means at time t equals 0, the slope needs to be positive 1. Could be. Right here, that's definitely a positive slope. But here it says that the slope, the velocity, is negative 2. That's definitely not true. Could not be negative 2. It could be 0.5, it could be, some other positive number, but it's definitely not negative. So we can stop right there and we can say, no. Velocity is the slope of the position curve at time t equals 1. The slope of the curve is positive, but the velocity is negative. With tables, we need to be a little bit more creative about how we figure things out. So here, if we're asked what's the particle's average acceleration from time t equals 0 to time t equals 3, we know that we're going to set up our average value formula. So 3 minus 0, integral from 0 to 3, a of t dt. The trouble is that the information that we have up here is information about velocity, and it's in a table, so we really don't have a whole lot. What we have to realize looking at this is that this is also the same thing as v of 3 minus v of 0. And that's, again, because the antiderivative of acceleration is velocity, and so we know that the integral is the antiderivative from the right bound to subtract the left bound. So that means that we can make this 1/3, and then this is just going to be v of 3 minus v of 0. And then v of 3 is 1. V of 0 is also 1. So it's 1/3 of 0, or just 0. And let's see, those units were those units ever given? Let's add in some units. good old meters per second. So average acceleration would be meters per second squared. We can also use tables to do other estimations when we're trying to work with the antiderivative of what we're given in the table. So let's take a look at a couple of those. Let's use Wright-Riemann sums. With equal intervals to estimate the position of the particle at time t equals 3 if the particle is at position, let's use x for our position variable, x equals 6 meters from the origin at time t equals 0. So we know that position at time t equals, let's say 3, it's going to be whatever position we're starting at, so we're starting at time t equals 0, plus however far it moves from 0 to 3. And some of this we can find. We're told that at time t equals 0, the particle is 6 meters. But to find this is going to take a little work because we don't have any equation to work with here, we just have these numbers. However, we do know that this is the area under the curve. But at the same time, we don't have a curve. We don't have a graph. So we have to estimate it using Riemann sums. So I have some information here. Let's do this in purple. I have some information here about this graph, even if I don't have a complete sketch. So I know this is 0, 1, 2, 3. It does go negative. 1, 2, 3. Negative 1, negative 2. When t is 0, so this is t and this is v of t. When t is 0, v of t is 1, 1, negative 2, 2, 0, and 3, 1. So I'm going to use Wright-Riemann sums, and I am going all the way from 0 to 1. So I'm going to do a little rectangle between 2 and 3. The right side is going to touch. So this is 1 by 1. 2 to 1, the right side is going to touch. So this is 1 by 0. And then 1 to 0, the right side is going to touch. So this is negative 2 and 1. So even though I don't have the exact graph, and I'm quite sure it goes, something like this and not exactly in little rectangles, I can still find the area of the rectangles. Negative 2 times 1 plus 0 times 1 plus, I do like to be inconsistent with that. Why don't I put this all down here where I'm not going to run out of room. Okay. Height times width plus height times width plus height times width right there. The area of the rectangles is negative 2 plus 0 plus 3 is 1. So that means this is going to be 6 plus 1. The particle is 7 meters approximately from the origin. And again, that's an estimate, but it's the best we can do given the information that we have. So once we know that we can use a Riemann sum to estimate the integral of velocity, that opens up all sorts of other things. So let's use a left Riemann sum Remember, if we were using trapezoid, it'd be the same thing. We just have to do 1/2 base 1 plus base 2, and then times the height. So let's do the interval 0 to 3. So average velocity, 3 minus 0, integral from 0 to 3, v of t dt. Again, we're not able to get this. We have to sort of estimate this from the table. So I'm going to do that same thing, but now we're using a left Riemann sum. So we've got one rectangle there, one rectangle there, one rectangle there. So this is 1, this is -2. The widths are 1. So the area is approximately 1 by 1 plus -2 times 1 plus 0 times 1, 1 plus -2, -1. So that's that integral. Now remember, we've still got this. So this is 1/3. Actually, I should say approximately equals on all of them. Approximately equals up there. So the average velocity is approximately -1/3 meters per second.